Good morning, children. So this topic which we'll be covering in this video is regarding stereoisomerism. So what exactly is meant by stereoisomerism? I have already discussed in the previous video that isomers can be classified as structural isomers and stereoisomers. Structural isomers we could understand because of the different structure or the way the ligands are attached to the metal atom. But in the stereo, when we talk about the word stereo means 3D spatial arrangements. Okay. And of course, the term isomerism you are pretty aware, which means the two compounds having the same molecular formula, yet they are different in the structure in 3D space. That is because of the difference in the arrangement of the ligands around the central metal atom. So this type of arrangement of the metal atoms and the ligands associated with each other is always spoken with respect to 3D space. So let's discuss the types of stereoisomerism. The first one is geometrical isomerism. This type of isomerism you have already studied in grade 11 for organic compounds. The concept remains the same. In geometrical isomerism, there are two types of isomers. One is cis and the other one is trans. So how do you differentiate between cis and trans? I will just take a few examples and explain you. Before that, I would like to mention one very important thing here, that this type of isomerism arises in heteroleptic complexes. And we already understood the term heteroleptic means the complexes containing two different types of ligands. So what are the geometrical isomers as for example cis and trans, and what is the difference between them we'll be discussing. Above that, you should also remember that such type of isomerism can be exhibited by both the types of complexes, that's with coordination number 4 and coordination number 6. So when we talk about 4, the coordination number 4, usually it's square planar with such type of isomerism. And for 6, the geometry so obtained is octahedral in nature. Okay, let me give you this example to make the things, clear to you. Fine. Now, when we talk about square planar complexes, that means let us take an example. It's a general example. M stands for metal atom, X stands for one type of ligand, and L stands for another type of ligand. As you can see here, the coordination number of such type of complexes would be 4, because in all there are 4 ligands, 2 of X types and 2 of L types. Now, what is the difference between cis and trans can be understood here very well. As for example, let us take this example of platinum NH3 2Cl2. Now in such type of complexes which we are talking about, basically the square planar. So here I have written down this example, that's platinum NH3 whole twice Cl2. What would be the name of this compound? Again ligand, and it's 2, so I'm going to use the term diamine, right? Dichlorido, fine enough. And the metal atom is your platinum, and oxidation state is 0 in this case. So what's the oxidation number? The total charge on the complex is 0 here. So what's the oxidation number? Again, X plus 0 into 2 plus minus 1 into 2. So the value and E of course equal to 0 because the total charge is 0. And I've already spoken that the total charge, if it's 0 on the complex, need not write it down. So X would land up as 2. So here I write 2. So that's the complex with me. Now if I want to write cis isomer of this, so cis means the two same type of ligands should be on the same side, as you can see here. NH3 that's the amine ligand, is on the same side, and chlorido, another type of ligands, are on the other side. So such type of isomers are called as cis, wherein trans you find the same ligand diagonally opposite to each other. So chlorido is aligned in one diagonal and amine is aligned in another diagonal. So such type of isomers are classified as trans. We have already learned this in grade 11 for organic compounds. If you remember which one is more stable, yes, trans is more stable than cis because the opposite poles are balanced. And one very important thing, if you calculate the dipole moment is 0 for trans because the two opposite poles are counterbalanced. Fine. So the net dipole moment comes as 0. Now when we talk about, so this is about your square planar. Another type of isomerism can be discussed in octahedral complexes. I'm talking about the same geometrical isomerism but in octa complexes. Octa complexes means the coordination number would be 6. So as it is very clearly mentioned here, X type of ligands are 4 in number, L type of ligands are 2. So the total coordination number becomes 6. Hence, its geometry is octahedral. Let me erase this for you so that I can use this space for writing the name of this complex. That's the octahedral complex mentioned over here. Okay, fine. Here we go. So, what could be the name of this IUPAC name? Let us see. Now, again, it's a positive charge. First, check the charge on the complex. As I said, it's a cation. Fine enough. Then we have heteroleptic complex, of course, because there are two different ligands over here, right? So such type of complexes are called as heteroleptic. We have already discussed before. And it's a cationic complex. So we'll start writing the name with the help of ligands, amine and chlorido. It's 4, so we are going to use tetra as a prefix. So here I'm going to use tetra, amine, right? Tetra, amine, dichlorido, because there are 2 atoms of chlorido ligand. Dichlorido. What's the metal atom? It's cobalt. Okay, fine. And the oxidation state I have to calculate for the metal atom. So it's X plus 0 into 4, then plus minus 1 into 2 equal to plus 1. So the value of X comes as plus 3. So here I'm going to write 3 in Roman numbers. So that's the IUPAC nomenclature of this octahedral complex. That's tetraamine dichlorido cobalt 3. So we clearly understood this. Fine enough. Now let us see the structure. How is it arranged in 3D space? Again, since we are talking about geometrical isomerism, it has to be cis and trans. Cis, as I said, 2 same type of ligands should be adjacent to each other on the same side. And in trans, 2 same ligands should occupy a perpendicular position to the plane. Now understand it very clearly. Since it's an octahedral, octahedral means it is going to have total 6 positions occupied by the ligand around the metal atom. So here is one plane for you. Here as well, this is one plane for you. To this plane, okay, we are making a perpendicular line, that is a line passing through this plane which is half above the plane and half below the plane. That's to mark over here. I'm talking about this one and this one. So in 2D space, this is your planar structure. To this planar structure, one chlorine and amine, chlorido and amine, are aligned perpendicular. But why do I call it as cis over here? Because, as I said, two ligands which are same should be adjacent to each other. Now where could you figure it out? Here is one chlorine and here is one chlorine. That is chlorido as a ligand to be named. So ligands chlorido are found adjacent to each other. Hence it's a cis type of geometrical isomerism. Wherein trans, I said, again it's a square planar space, fine. To this we have a perpendicular line passing, and to this perpendicular line we have placed two same ligands, that's chlorido. So two perpendicular positions, that is one above the plane and the other one below the plane, if satisfied with the same ligand, same type of ligand, it's said to be trans. Wherein when two same ligands are present adjacent, okay, they are present which position? Adjacent position to each other, they are said to be cis. So this is how we decide cis and trans in octahedral complexes and as well as in square planar complexes. So I think hopefully it is clear to you. You can just see it once again. I'll just enlarge the image for you. Fine. Now let us understand another type of condition which can arise in octahedral complexes, where we have octa means again 6. In the previous example, I'll just brief you. Yeah, here the type was 2 plus 4. What is 2 plus 4? 2 atoms of one type of ligand, 4 atoms or molecules of another type of ligand. But here they are equal in ratio. That is, both the ligands are 3 in number. So this type of complex, M here stands for the metal atom. A is one type of ligand, B is another type of ligand. So both the ligands are 3 in number. So this example is highlighted over here. Let us try to name it. Since there is no charge mentioned, that means the charge is supposed to be taken as 0. So again, two ligands are here. One is amine and the other one is nitrito N, because nitrito is an ambidentate ligand. Since its coordinating atom is nitrogen, so we are going to mention it as nitrito N. So how do we name it as? Now it's 3. 3 means tri. So triamine, right? Triamine, fine. Then again it's 3. So I'm going to use again tri nitrito, because it's an anionic ligand, so ending with O hyphen N. N signifies that it's an ambidentate ligand and bonded with the metal atom through nitrogen atom. Fine. Then again the central metal atom is cobalt. Okay, I write here. And then I need to calculate the oxidation state of the central metal atom. So I'll use this space for calculation of oxidation number. Again, cobalt, I'm going to put it as X plus amine 0 into 3 plus nitrito, it's -1, the charge, and into 3 equal to 0. So the value of X lands up as +3. So here I'm going to write 3 in Roman numbers. So that's the IUPAC. I think a lot of practice I have given you by now for IUPAC. Hopefully you are thorough with it. Okay, fine. Now in such type of complexes, we don't use the term cis and trans. Make a note of it. We don't use the term cis and trans. Indeed, we have the term called as facial isomer and meridional isomer. So FAQ and MER are the two conventions which is used for such type of complexes which are in the form of MA3B3 type. Now, how do we define it as, and what is the basic structure? Now, why do we call it as facial? We call it as facial because the same type of ligands occupy the corners of a octahedral face. I can highlight here for you. They occupy the corners of octahedral face. Now, where is this octahedral face for you? Here in this figure, this is the octahedral face, right? So the corners of octahedral face is occupied by same type of ligands, that's nitrito N. Hence, it is called as facial isomer. Of course, it's a geometrical isomer. Whereas in MER, okay, that's meridional. Oh my god, this is pretty different from facial, but it's very easy to understand. That's the position of the same ligands, okay, around the meridian of the octahedron. Now, where can you finalize the meridian? This was the octahedral face, I said, and meridian is this. Okay, so now you can see the geometry as this. So here, this type of meridian where you see that the position is occupied by the same ligands. So here nitrito, 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 whereas here you can see again the same ligands, that's amine. So here I think I can make it darker for you. This is NH3 here. Here also you have NH3 and here also you have NH3. Whereas this is NO2 for you. This is NO2 and here also NO2, right? Wherein here you had NO2 along the face, octahedral face. So I think it's very clear to you how to figure out your what you call facial and meridian. So here I have a little bit darken it for you so that it's easy for you to understand. Fine enough. Now let us quickly go through optical isomerism. Geometrical isomerism is over for you. When we talk about optical isomerism, this also you have studied in grade 11. Here we have a concept of enantiomers. What are enantiomers? Non-superimposable mirror images. So remember, optical isomers are non-superimposable mirror images of each other and they are termed as enantiomers. For example, if you look into the mirror, your left hand appears as right and right appears as left. So that those two hands, the image of your right hand which appears as a left hand in the mirror, can you superimpose? No. These images are non-superimposable. Hence, such type of isomers are called as optical isomers. So, very important point to be noted down here is cannot be superimposed. Okay, and there is one term called as chiral. What is chiral? In organic chemistry, you have learned chiral carbon atom is a one which is bonded with 4 different groups. Okay, so A, B, C and D are 4 different groups. So such type of atom is said to be chiral. And the two forms which originate because of optical isomers or isomerism, One form is called as dextro and the other form is called as levo. So dextro means turning the plane polarized light towards right, and levo means turning the plane polarized light towards left. In detail, this all will be again talking in chapter 10, that's organic chemistry. Okay, so right now you just keep in mind that there are two forms, dextro and levo. Dextro means when the plane polarized light gets deviated or rotated towards right, and L stands for left. So such type of optical isomerism, as I said, is observed in octahedral complexes and particularly involving ditentate ligands. That is the ligands with two donor atoms bonded to the metal atom at the same time. So let us see the example over here. Yeah, here we go. So one beautiful example over here is, yes, this one. That's COCl2En whole twice and the charge is 2 plus. Again, I would like to write the IUPAC for you so that you are very thorough with it. Since it's 2 positive, it's a cation, no botheration because cation I have to cite first. Let me check out the ligands. It's chlorido and ethane 1,2 diamine arranged in alphabetic order, pretty enough. So I'm going to start with prefix di because there are two chlorido. So dichlorido, right? Dichlorido. Again, it's two molecules of ethane 1,2 diamine, but I can't use the prefix di. I'm going to use prefix bis. So bis hyphen ethane, yeah, 1,2 diamine. So I have written down here for you. And the metal atom is cobalt. Again, the oxidation state, I need to find it out. So here it's X plus Cl is -1 into 2. Again, it's 0 into 2 equal to +2. So the value of X lands up as 4. Is it or not? So here I'm going to write 4. And I'm going to write ion here because there is no primary valency mentioned here. There is no counter ion mentioned here. So in such cases, when you have 2 plus charge, you usually end up with ion. Okay, even if you don't write, it's perfect, but it's better to write ion in such cases. Okay, fine. Now how do we explain the optical isomerism here? As I said, it would be dextro and levo. And one another very important thing here is, along with optical isomerism, there is an origination of geometrical isomerism as well. That's cis and trans. Let us understand. So first of all, in such complexes, we would talk about geometrical isomerism followed by optical. So when I say geometrical isomerism, I made it very clear we have two forms, that's cis and trans. How do you call it as trans? Because the same type of ligands are opposite to each other. Now see, ethane 1,2 diamine is left, another one is towards the right. Chlorido up and down. So they are balanced. This is a trans form. Wherein if you want to write the cis form, it's adjacent position. So chloridos have occupied the adjacent position. Ethane 1,2 diamine have occupied another adjacent positions. And why are they mentioning here with the ring? Yes, very clear. I have mentioned before that didentate ligand coordinate to the metal atom at the same time with the two donor atoms. Henceforth, this is a type of chelation observed, which we have already discussed before. So now, cis-trans concept is clear to us. What about optical isomerism? Now listen carefully. Trans. If you find out the mirror image of trans, what will it turn up? The left becomes right, top becomes down and down becomes top. So, but when we do this, aren't we ending up with the same structure what we had before? Of course, without any doubt, yes. So, what do we conclude? So, trans isomers will not exhibit optical isomers, whereas cis will do that. Okay, so when I say trans will not exhibit any optical isomerism, why? Because they have superimposable mirror images. What do they have? They have superimposable mirror images, as I have shown over here. So remember this point, trans isomers are optically inactive. Okay, so to be mentioned. Okay, what about cis? Yes, cis will exhibit. So in cis isomers, there will be optical isomerism observed because they will form non-superimposable mirror images. Let us see here. Now I said there will be exchange from left to right. Now two chlorine atoms are present here adjacent to each other. So what will happen if you flip it? If this is right on the right side, they will come to the left side, as I mentioned over here. Again, ENs here, they were towards the left side. Now they will move towards the right side. If you take out this isomer, okay, if you pick this isomer as I said and try to impose on this one, will they get imposed? No. So they are called as non-superimposable mirror images. So if one is dextro, the other one would be levo. And what are they called as? They are called as enantiomers. I'll write down here. They are called as enantiomers. So enantiomers are non-superimposable mirror images of each other, right? So the point to be noted down here, I have mentioned very clearly for you so that you don't forget this ever, that trans isomers are optically inactive whereas cis isomers are optically active. So in such type of complexes, as I mentioned over here, the total number of isomers, if they ask you, this is a very, very important board question, okay? You are going to write the number as 3. How 3? 2 geometrical isomers, that is 2 originating from cis and trans. And the third one, because cis is going to be observed as optical isomers as well. So in all, there are 3 isomers to name. Here we have 1, 2 and 3. This one we don't, because this is same as compound 1. I think this is pretty clear to you. So here I have one example for you. Draw the structures of optical isomers in this case. So again, the optical isomers, as I have shown over here, since it's oxalate, again didentate, it is going to occupy the positions like this. But here the mirror images can be observed because left becomes right and right becomes left, right? So with this we come to an end, and here I have a question for you. I'm not going to share the answer right now. Draw all the isomers, whether geometrical and optical, of these 3 compounds. So take up your notebook in your hand and start down with the answer. So here we come to an end of this video. I want to get the answer of this. That we'll be discussing in interactive session. Thank you all.